Hi everyone, my name is Yuzechi. In this video, I will walk you through our paper, Accelerating SSP for Power law graphs. This research is performed in Professor Jason Cong's lab at UCLA. Single source shortest path, or SSSP for short, is a basic but important problem. Many real-world applications use SSSP. Many related shortest path problems, for example, single pair shortest path, can be solved using the same algorithm used for single source shortest path. The problem formulation is quite simple. For a given positive weighted and directed graph G and a source vertex U, the SSSP problem aims to find the shortest path tree from U. This includes the shortest distance from U to each vertex and the parent of the vertices. To solve the SSP problem, Dijkstra's algorithm has been known for many decades. The algorithm begins with setting the distances of all vertices to infinity and making the parents of all vertices to null, with the exception that the root vertex has distance 0 and its parent is itself. In the example shown here, the root vertex is A. After initialization, the root vertex is marked as active. The algorithm then iteratively finds the active vertex with the minimum distance, marks it as final, traverses its neighbors, and updates the neighbors if it is necessary. The updated neighbors are then marked as active, and the next iteration begins. The algorithm terminates when there is no more active vertices. It has been proven that each edge will only be visited at most once with Dijkstra's algorithm, so no edge traversal would be redundant. To implement this algorithm efficiently, we usually use a priority queue to store the active vertices, which basically are the frontier of the graph traversal. The usage of priority queue can create challenges for optimizing the SSP algorithm. The problem is that it is hard to create priority queues with a large capacity. This may be okay for planar graphs because their frontier is small and it does not scale with graph size. However, for power law graphs of similar sizes, their required frontier sizes are much larger than planar graphs. Even worse, the frontier size increases when the graph size increases. Meanwhile, many real-world graphs have very skewed degree distribution and have the same properties as power law graphs. The Graph 500 benchmark for SSSP also uses power law graphs. In summary, accelerating SSP for power law graphs is challenging. This is because, first, SSP requires a priority queue. Of course, there are algorithms that do not require a priority queue. For example, the Bellman-Ford algorithm. However, such algorithms require much more edge traversals. We will show later in the experimental results that although various graph processing systems can achieve much higher graph traversal throughput than our work, the high redundancy eventually leads to a poorer overall performance. For planar graphs, the priority queue is not imposing too many problems because the priority queue doesn't need to have a very large size and one can use on-chip implementation. For example, a pipeline priority queue to solve the problem. The situation is very different for power law graphs, which requires a much larger priority queue that stores vertices in off-chip memory. Worse still, such a priority queue must still have a high throughput to sustain the highly parallel graph traversal. Another challenge is the random accesses implied by the priority order traversal. There are many techniques to confine the random accesses to a small interval of vertices, but they won't be helpful here because we need to follow the order specified by the vertex distances. Otherwise, the redundant edge traversal can easily kill any performance improvement obtained from reordering edge traversal. To the best of our knowledge, our work, Splat, is the only accelerator that implements work-efficient SSP algorithm with an application-specific customized vertex cache. The key to addressing the challenges is to relax the definition of priority. Instead of using the strict priority definition of the distance from the root and using the boundary heap, the pipeline heap, or the systolic priority queue, we can relax the definition of priority and divide the vertices in the queue into several buckets based on their tentative distance and their pre-selected delta. Different vertices with the same bucket are considered to have the same priority, making it possible to create a large priority queue with the high throughput. Before I present the architecture of Splat, I'd like to briefly go over the algorithm. Splat uses a variant of Dijkstra's algorithm. The input, output, and the initialization is the same as Dijkstra's algorithm, which we have discussed earlier. To fully exploit potential parallelism, Splat aggressively pop vertices from the queue and traverse their neighbors in parallel. Different from Dijkstra's algorithm, after a vertex U is popped from the queue, we check if we already know a path to U with a smaller distance. If not, we traverse the neighbors of U, compute new tentative distances to the neighbors, and update the neighbor vertex if necessary. In line 8, we skip the parent of U because we know the parent of U must have a smaller distance than U. If a neighbor vertex is updated, we push the updated vertex to the queue so that its neighbors will be traversed in the future. The algorithm terminates when no vertices exist in the queue. The Splat Accelerator consists of 3 components: the coarse-grained priority queue, or CGP-queue, the customized vertex cache, or CVC, and the edge fetcher. The CGP-queue handles the push and pop operations. The edge fetcher traverses the neighbors and computes the new tentative distances. The CVC handles 2 different operations. The operation shown in line 6 is read-only, which filters vertices with stall values when popped from the queue. We'll call this operation CVC filtering. It receives inputs from the CGP queue and sends the output to the edge fetcher. The operation shown in line 10 and 11 must be done atomically, which updates vertices if the new path has a smaller distance. We'll call this operation CVC updating. In contrast to the filtering operation, the updating operation receives inputs from the edge fetcher and sends the output to the CGP queue. This slide shows the Splat architecture implementing the algorithm in the previous slide. The 3 major components are each internally partitioned and parallelized. The partitioning is done based on the modulo of vertex IDs. Since each vertex may have neighbors in any partitions of vertices, we use a multi-stage network to route the vertices to the correct partition. Here is an example using the same graph we used earlier. Note that I colored the edges in the figure on the right-hand side consistently with the boxes representing edges on the left-hand side. We start with initializing the vertex attributes and traversing the neighbors of the root. The first traversed edge is the green one, which updates the distances of D from infinity to 8. The updated vertex D is pushed to the CGP queue. Meanwhile, the other neighbor of A, the blue edge, updates the distance of B from infinity to 3. The updated vertex B is also pushed to the queue. The queue finds that vertex B has a smaller distance, so it pops B and sends it to the CVC. The CVC checks that the distance of B has not been updated ever since it was pushed to the queue, so it sends B to the edge fetcher for traversal. Vertex D, as the neighbor of B, is then traversed and sent to the CVC. The CVC updates the distance of D from 8 to 5. Then, when the older version of D is popped from the queue, the CVC finds that we already know a smaller distance of 5, and it discards the version of D with the distance of 8. The newer version of D is pushed to the queue eventually, and is later popped, filtered by the CVC, and sent to the edge fetcher. The neighbor of D is then traversed, and we update the distance of E in the CVC. Vertex E is pushed to and popped from the queue, and the neighbor of E is traversed. When the CVC receives the vertex B with the distance of 13, it discards this update because we already know a shorter distance of B. The algorithm terminates at this point, generating the same correct result as the extra's algorithm. As illustrated just now, the customized vertex cache is an important component of Splat. It is implemented as a direct map read-back cache with fully pipelined operations that hides off-chip memory latency very well. This is achieved using the asynchronous memory interface that is available only in the extended HS language Java. Unlike a standard application agnostic cache with read and write operations, the CVC implements two application-specific operations directly, namely the update operation that receives vertices from the edge fetcher and updates vertices atomically, and the filtering operation that receives vertices from the CGP and filters stall vertices when appropriate. Both operations are helpful to reduce redundancy when the CVC already knows a smaller distance of a vertex. Our CGP is inspired by the double-ended queue, or DAQ, data structure, which is a linked list of fixed-size arrays. Like the DAQ data structure, each bucket in the CGP is divided into chunks with a fixed compile-time configurable size. Unlike the DAQ data structure, CGP manages the chunks using a chunk priority queue. Since the size of each chunk can be very large, for example, 1024, the size of the chunk priority queue is much smaller than the capacity of the CGP, so it can fit on chip. The CGP buffers one chunk for each bucket on chip and spills excessive chunks to the off-chip spill memory. The chunk priority queue remembers the location of each spilled chunk so that the chunk with the smallest distance can be refilled from the spill memory when appropriate. The chunk buffer is the key to achieving the two design objectives for the CGP. It exposes two levels of parallelism at both inter-bucket and intra-bucket levels. The inter-bucket parallelism enables pushing vertices to different buckets in parallel, while the intra-bucket parallelism allows popping multiple vertices from the same bucket at once. The intra-bucket parallelism also makes it possible to spill and refill the chunks with a high memory bandwidth utilization by coalescing the memory accesses. The chunk buffer keeps track of the size of each buffered chunk. When the buffer of a chunk is almost full, that chunk will be scheduled for spilling. The location in DRAM and the priority of the spilled chunk will be pushed to the on-chip chunk priority queue, or the CP. When a chunk becomes almost empty, the chunk buffer checks the CP to see if we should refill it. Here is an example. Let's say the first chunk spilled to DRAM belongs to bucket 2. Later, a chunk belonging to bucket 0 spills to DRAM, which has higher priority than the previous chunk. Therefore, the entries in the on-chip CP is updated, but the off-chip data is not moved. Then, another chunk is spilled to DRAM. There can be multiple chunks belonging to the same bucket. Their relative priority is arbitrarily determined by the CP. When the on-chip chunk buffers are being exhausted and refilling is necessary, the chunk belonging to bucket 0 will be refilled first. In practice, the CP can hold up to 256K entries, and each chunk contains 1024 vertices. The edge fetcher is relatively simple. It traverses the neighbors of a vertex using the offset and degree stored in the vertex attributes and computes the new tentative distances of the neighbors. This slide lists the datasets used in the experimental evaluation. We first evaluate the CGP. This figure shows the percentage of spilled vertices over the total amount of vertices pushed to the CGP, which are collected by the performance counters inserted to the accelerator. We can see that the spilling mechanism is very effective. Most datasets leverage spilling to hold the large frontier. The scaling trend from G515 with 32,000 vertices to G520 with 1 million vertices demonstrates the scalability of the spilling mechanism. Therefore, we think we have achieved the high capacity design objective for the priority queue. This slide shows that we have also achieved the high throughput design objective. The figure shows that the CVC is idle for very few percentage of time. The CVC may be idle either because the CGPQ is empty or the pop throughput is too low to generate requests to the CVC. Low idling indicates that the CGPQ pop throughput is sufficiently large. Moreover, the performance counters also show that the CGPQ never stalls the CVC due to insufficient push throughput. Therefore, we have achieved both design objectives for the CGPQ. Next, we will evaluate the CVC. We can see that overall hit rate of the CVC is high. The write hit rate is lower than read because most memory accesses are read-only. We think we have achieved the goal to create a fast memory system. This slide shows the percentage of vertices discarded by the CVC. Each edge may either be discarded by CVC updating right after being traversed in the edge fetcher, or it may be an active vertex and be pushed to the CGPQ. When the active vertices are popped from the queue, it may be discarded by CVC filtering or may be sent to the edge fetcher as the source vertex. We can see in the figure that the CVC is very effective in removing redundant edge traversal. This figure further shows that Splat is very effective in terms of removing redundant edge traversal. High throughput and high capacity CGPQ and the fast and redundancy removal CVC leads to a high throughput. This figure shows both the traversal throughput and the algorithm throughput achieved by Splat. The traversal throughput counts all traversed edges, including ones visited many times, while the algorithm throughput only measures the number of edges in the connected component of the root. This is the metric defined and used by Graph 500. This table compares Splat with other systems. Galois is a state-of-the-art concurrent graph library designed for graph analytics as well as other irregular applications. Splat outperforms Galois running delta stepping on multi-thread CPUs by up to 2.6 times. Compared with one of the latest GPUs, Splat achieves up to 0.9 times speedup over the GPU, which has 4.1 times power budget and 3.4 times HBM bandwidth. Compared with other FPGA-based accelerators, Splat is up to 4.9 times faster. This is because the baseline FPGA accelerators do not support removing redundant edge traversal as Splat does, and while they can achieve higher traversal throughput, the algorithm throughput is lower. Note that to make a fair comparison with non-HBM FPGAs, we ported Splat from U280 to U250 with appropriate resource constraints. Besides, we evaluated Splat using the Graph 500 benchmark. Splat can be placed at the 14th place on the June 2021 list with only a 45 watt power. In comparison, the 13th system on the same list uses an 8-node cluster. In summary, Splat is a performant and energy-efficient FPGA accelerator for the single-source shortest path problem. Two components in Splat are key to achieving the acceleration. The coarse-grained priority queue uses an on-chip priority queue to orchestrate the off-chip memory accesses and enables high-throughput priority graph traversal with a large queue capacity. The customized Vertex cache implements two application-specific operations to reduce the amount of off-chip memory access and improve the throughput of random memory accesses imposed by priority order graph traversal. Written in Tapa HLC++, Splat is easily portable to a different FPGA with a different configuration, as we just demonstrated in the previous slide. Even better, Splat is open source, not only with the paper artifacts and pre-built bit streams, but also the full source code and its history on GitHub. You are very welcome to review, download, and modify the implementation. Feedbacks and suggestions are much appreciated. This slide shows the references. That is all I have. Thank you for listening.